Good evening, everybody. Hi, I'm Silas Laycock, and it's my pleasure to welcome you to the Schiller Observatory's Public Observing Night for the month of October. And tonight we've got graduate student Nick Sorabella, who's going to be giving a talk about the search for life in the universe and the prospect for what it may be. And we're also going to hear from undergraduate Liam Neely, who's going to be talking about what's up in the sky tonight, part of his usual sequence on that. Thank you for coming out with the bad weather. For those of you watching at home or watching the recording, there won't be any observing this evening because it's pouring rain here in Lowell. So let's see, what other information we have to impart. If anyone would like to get in touch with the observatory, if you'd like to use the telescope for your group or club, or just learn how to use it yourself, or learn about the opportunities to work with the observatory academically or for other purposes, you can send email to observatory@uml.edu and one of us will get back to you. So without further ado, I'll get out of the way and hand it over to Liam. Thank you.
Okay, so, well, what's in the sky tonight? Unfortunately, as I was brought up, it's mostly clouds, so I won't be able to see anything, but hey. So, it's like a semi-bright dot, a little bit. You should be able to see it. If you have you can use like an app on your phone to be able to point out exactly where it is. Easy to see. It's 9.5 AU away from the sun. An AU is an astronomical unit where 1 is the distance between the Earth and the sun. So it's over 9 times the distance the Earth is away from the sun. It has at least 62 moons. And Titan is the biggest one of its moons, and if you have a telescope, you can sometimes see Titan. There's also Jupiter, which is also visible with the naked eye, same area-ish. It'll be much brighter. It's 5.5 AU away from the sun. It's 764 times the size of the Earth, and it has 4 moons that you are able to see. So it's Callisto, Io, Ganymede, Europa. Depending, you can see them if you have a telescope. Depending when you look, some of them may be behind it. But you can still see all 4 in a good night. For some deeper sky objects, you can't really make out with naked eye. If you have a telescope in a dark area, you might be able to see them. Or if it wasn't cloudy out, we have a camera attached on the end of our telescope. So we can do long, 60-second exposures, and then we will be able to make them out. So one is because Ghost Galaxy, it's Halloweenish time, so I definitely didn't search for objects that have ghost in the name for this presentation. So it's a field galaxy, so it's not really in a group of gravitationally attracted galaxies. It's 10 million light years away, and it's mostly made up of younger stars. We also have Fireworks Galaxy. It's face-on spiral galaxy, so if you take an image, you can see the spirals of the galaxy. This is 25 light years away from Earth, 25 million light years, slightly different. And it's 40,000 light year diameter, which is about a third the size of the Milky Way. You can see the Phantom Streak Nebula, which is 7,000 light years away. It's a planetary nebula, so how planetary nebulas form is there's a red giant. At the end of its life cycle, it releases off gas. The red giant becomes a white dwarf. And so you can kind of see a white dot in the center, which is that, and the gases are slowly expanding away. And as a whole, the nebula is heading away from us at 4.2 kilometers a second. There's also the Ghost of the Moon Nebula, which is 1,500 light years away. It is also a planetary nebula. It's 0.4 light years across. There's the Anglefish Cluster, which is a globular clusters of stars. So it's just a bunch of stars that are all really close together. It's 13,000 light years from us. It's a relatively young cluster, which is 9 to 10 billion years old, so still pretty old, but on the grand scheme of things, not that old. We have Great Pegasus Cluster, another globular cloud star cluster. It's one of the denser star clusters in the Milky Way, and it has a planetary nebula on the inside of it, which is pretty cool. So that's what I have for Up in the Sky. October 27th, we are hosting another open night type thing, a spooky open night. So we'll just be down at the observatory, looking at various objects. There'll be some candy treats, and we'll have a raffle where you can get a night to use the observatory. QR code if you want to scan it, you can register, and then we'll email you about any updates due to weather. Does anyone have any questions? Yes, you can. Right, so then I will turn it over to Nick. Yeah, same thing.
What does the sound the room like?
Up to you. You should be able to see everything, but looks like Santon's got that. Let's see. Ooh. I think that's good. Need to be able to see something, right? Well, hello, everyone. To our virtual audience, I don't know if you can actually see me or if you can only see the slides, but I'm Nick Sorabella. I'm a fourth-year grad student here at UMass Lowell. I'm standing very far away from you guys right now because apparently I have to stand underneath this thing in order for the mics to pick up. So I'm going to use this laser pointer to show you guys things over there. So today I'm going to be talking about life in the universe. Now, that's a bit of a loaded phrase because when I say life in the universe, your minds are inexorably drawn to these little guys, right? The little green men, aliens. And, you know, talking about aliens in a scientific setting in a presentation like this, you probably think of somebody like this guy from the, in quotation marks, History Channel, trying to convince you that the pyramids were in fact built by the aliens, you know, that there were flying machines in 10,000 BC, stuff like that. When you think about someone talking about aliens, they probably look something like this, right? They're the conspiracy theory people. They're trying to talk to you about flying saucers, you know, cow probes, and about the alien baseball team that plays at the baseball field at Area 51. That is a real photo, by the way. That is like a top 10 random trivia fact that I have, is that there is actually a baseball field at Area 51. If you look like a little bit above it and to the right, there's a tennis court too. I guess when you're stuck on an airbase in the middle of nowhere, you need to do something to entertain yourself. So they formed their own baseball teams, which is kind of cool. But we're not here to talk about any of that stuff, right? That's all the conspiracy theory things. We're here to talk about life in the universe. We want to talk about like the actual scientific things that we're studying, whether it be the conditions that are required, or at least that we think are required for life to come about. We're going to talk about the search for life, like the different telescopes and methods by which we're doing that. We're going to go into a little bit of this fun thought experiment trying to estimate how many intelligent civilizations there are in the Milky Way right now. And then, to cap things off, we're going to talk about some of the things that we're doing here at UMass Lowell for research, looking for life or the possibility of life in more extreme circumstances than what we have here on the Earth. Now, before I get started with life in the universe, we have to talk about the universe first. For starters, the universe is 90 billion light years in diameter. That sounds really big, right? It has the word billion in it, but what's a light year? Now, somewhat confusingly, a light year is not a time, it's a distance. It's how far a beam of light would travel in a single year. Now, we know light is fast. It's the fastest thing that there is, right? If I had a light beam and I had it go around the Earth, like in a circle around the Earth, it would go around the Earth 7 times in 1 second. That's pretty fast, right? Now, what I'm here to tell you, 90 billion light years, that means that it would take a beam of light 90 billion years to go from one end of the universe to the other. That's not taking into consideration the fact that the universe is actually expanding, so it's always getting bigger. But if we just say that it's 90 billion, it's not moving at all, it would take 90 billion years for that beam of light to go across it. The universe is a big place. It is, kind of by definition, the biggest thing, right? Because it's everything. Based off observations, we know that there are at least 100 billion galaxies in the observable universe, each containing 100 to 1,000 billion stars, so a trillion stars. How many stars is that? Again, that sounds like a really big number, and I don't expect our minds to comprehend what that is, right? There's this very common, example that people give when talking about this. I don't know who actually sat down and did the math to figure this part out. It might have been Carl Sagan, because I know he talked about it on the original Cosmos, but the saying goes that there are roughly 10,000 stars for each grain of sand on every beach of the Earth in the observable universe. That is a lot of stars. I want you to think, I'm assuming you haven't been to every beach, right? I mean, that's a lot of beaches. That could be a life goal, is to go to every beach on the planet. But just think about one for a second. That's a lot of sand, right? I can see you laugh. Have you tried counting all of the sand at the beach? I don't think so, right? Yeah, better things to do. Now, if you took a big bucket of sand, now we've condensed the amount of sand, it would be like taking that bucket of sand and then filling 10,000 more buckets, and that's how many stars there are equivalent to that one bucket of sand. There are a lot of stars in the universe. And as many stars as there are, we are actually, based off observations we've made, pretty confident that there are very much, or there are more planets than stars in the universe. This is an important fact, because as far as we can tell, because we happen to be living on one, life needs something to stick to. It needs a planet from which it could, come into existence. It's not just floating out in space. Could it be just floating out in space? Maybe. But, we're the only example of life right now. And we have a planet, right? We're on a planet. So the more planets there are, the more potential there is for life to develop elsewhere. And there are quite a few planets in the universe. The universe is also a very old place. Based off our current estimates, the universe is roughly 13.8 billion years old. That's pretty old, right? Now, the Earth only showed up 4.5 billion years ago. This means that there were 9.3 billion years before even our planet existed. Now, as for us, we're much more new than that. Our earliest human ancestors, Homo erectus, came into the picture roughly 3.6 million years ago. Million. We're on the scale of billions of years where we weren't around. So it is an old place. So the question that I ask of all of you, we now know that the universe is a very big place with a lot of planets where life could develop. It's a very old place. There's been a lot of time at which life could develop. The universe is so old, it has so many planets where life could have developed, then why don't I see Chewbacca flying the Millennium Falcon overhead every night going up to blow up the Death Star? Where are all the aliens? This is a very important question when talking about the life in the universe. In fact, it's so important and so well known that we gave it a name. It's called the Fermi paradox. And you might be able to tell based off that word paradox, we don't have an answer to the Fermi paradox. It's an unanswered question. And I'm not here to tell you that I have an answer to the Fermi paradox. If I did, I'd be leaving to go accept my Nobel Prize right after this presentation, right? And the Fermi paradox leads to another important question about our place in the universe. And again, it's one I don't have an answer for you. Are we alone? It's a tough question to deal with, right? And I'm going to help you guys through this. We're going to talk about the conditions that life needs in order to thrive. or to come into existence. And we're going to go forward with that. So to start, we're going to talk about the principle of mediocrity. This is like a top 5 science term for me. I love this. I don't know why. It's like right underneath spaghettification. Like it's up there, right? So what is the principle of mediocrity? Well, to sum up rather simply, the laws of nature are universal. Well, what does that mean? That means regardless of where you are in the universe, the laws of science work no matter where you are in the universe. They are universal, called the universal laws of nature. So the laws of physics that I have here on the Earth should be the same laws of physics that I have on Venus or on the sun or near a black hole. Now, we call it the principle of mediocrity because, technically speaking, we haven't been to these places. So you could argue that we don't actually know. I mean, I don't plan on going on the surface of the sun anytime soon because I would be on fire, but that's why we could say it's mediocre. But based off observations we've made and science experiments that we've done, we're pretty confident that the laws of nature that we have here are the same elsewhere. Now, I took a course my freshman year of college at Bentley University titled Life in the Universe. In fact, much of this talk is a kind of condensed version of that course. And my professor there, his name is George Fishman, he had a way of applying the principle of mediocrity to life in the universe, or our search for life in the universe. He stated pretty eloquently that if it works here, why not elsewhere? If it works here, why not elsewhere? So we only have one example, one place where life has developed and has formed intelligent life. Anyone want to raise their hands and tell me where that place might be? Don't be shy. Don't be afraid to answer. It is too easy. It's the Earth. You're standing on it right now. This is it. This is the only place that we currently know of where there is life in the universe. We are a model example of the conditions that are required or that can lead to life. Now, the universe, as we have established, is a big place. There are a lot of places that are not like the Earth. I mean, look at all the planets in our solar system, right? They're very different from us. But life works here. We know it works here. So we can decide to rule out a lot of the places. If we decide to search everywhere, we may never find life because the universe is a big place. If we focus on places that are similar to Earth, that have suns or stars that are similar to our star, we might be able to narrow things down and find life elsewhere. So that begs the question, what is life as we know it, or LACI for short? There are 3 main components to life as we know it. The first is a major source of energy. Energy is important. Energy, heat, it helps drive chemistry. First it drives physics. Physics drives chemistry, and then chemistry drives biology. Chemical reactions are needed for life to happen, so a major source of energy is required to make those things occur. The second thing, as far as we can tell, is liquid water. Regardless of where we are on the planet, if we find liquid water somewhere, there's life. It's just like required. It's there all the time. Why not liquid anything? Why can't I have liquid sulfuric acid? Well, liquid sulfuric acid destroys organic molecules and compounds, stuff that we're made out of, or things that are required for life. Water does not do that. It doesn't dissolve things, it doesn't destroy things, and it's a great medium for chemical reactions to occur. And again, chemistry is kind of what leads to biology. So in order for life to develop, you need some kind of chemical reactions to start. The third thing is a little less obvious. It's carbon-based organic molecules. We are all carbon-based, like our skin, our bones, everything that makes up us. Carbon is the element that kind of bonds everything together. The reason for that is that it is great with bonding with all these other kinds of elements. Now, could life exist in places very different from the Earth? Is carbon-based organic molecules required? Maybe not. I don't know. I haven't seen any other place, right? Carbon is great because it can bond to all the other elements, or most of the other elements, and it can form these more complicated molecules and structures. But we also know that silicon can actually do a very similar job to carbon. Is carbon better? Maybe. I mean, it worked here, right? And we don't have silicon-based life here. But it is possible that somewhere else out in the universe that there are silicon-based life. But again, we're focused on life as we know it. And this is what we have here. And these are the three things that we think are required, like the three major things that are required to form life. So what does the Earth have going for it? What is our major source of energy? Does anyone have any guesses on that? You mouthed it. You're going to say it now. It's the sun, yeah. It's that big bright thing in the sky. The sun provides light, it provides heat to warm our planet. Think about plants. Plants get their food using photosynthesis. It's turning light directly into energy that lets them, live. So you have the plant, cow eats the plant, we eat the cow, or if if you're vegetarian, you skip the cow, you just go right to the plant, you are still getting your energy from the sun, one way or another. So you're all solar powered, in case you didn't realize that. What about liquid water? Do we have any of that stuff on this planet? Has anyone seen any of that? Well, according to this picture of this pond that I took, yes, there is plenty of liquid water on here. If there wasn't, that'd be a problem because we kind of drink that to survive. Fun fact, I took this picture about 5 minutes after asking my girlfriend to marry me. More fun fact, she said yes, so it was a really good day for me. Carbon-based life forms, do we have any of that? Well, I kind of gave that away because I already said you're made of carbon, right? But is there any other example of carbon-based life? Liam's already smiling. Well, according to this picture of my family's dog, yes, there is more carbon-based life out there. That was the silliest photo I could find of her. I made that a challenge, so this is the one that you guys got. Now, are there other forms of energy that life uses on the Earth? Believe it or not, yes. Sunlight does not get everywhere. If you go down to the very bottom of the ocean, there's just too much water for light to get through all of it. So there's no light down there and there's no energy from the sun going down there. But there is still energy in some form. And it takes the form of these hydrothermal vents on the ocean floor. These are basically like underwater volcanoes, and they're kind of spewing heat up into the water above it. And the heat that's being provided by these underwater volcanoes are helping drive the chemical reactions required to sustain life down there. If you look closely, there's a little tiny crab there. So he's living next to this hydrothermal vent. He's eating whatever else is living by this vent here. And this is actually important, these vents, because there are places even in our own solar system where sunlight isn't going to really be the major source of energy, but they might have everything else going for them. They might have liquid water. There's a chance that there's organic molecules. It's just missing the sunlight. And there's no better example of that than Europa, which is one of Jupiter's moons. Now, Europa has this really icy surface. And ice, that's not really what we're looking for, right? I said liquid water. But underneath this icy surface, we are pretty confident that there is a very large subsurface liquid water ocean. In fact, it has so much water in it, at least we believe there's so much water in it, that it might have more water than we have on the surface of the Earth. So it is quite a deep ocean. Now, sunlight can't penetrate through this icy surface. It's like miles deep of ice. There are some places where it might be a little less deep, but in general, sunlight isn't getting it. But there can very likely be these hydrothermal vents on the ocean floor. We know that there is some tidal interaction with Jupiter, which may be driving some volcanism that leads to these hydrothermal vents. So assuming there's hydrothermal vents, and if there are organic molecules, and if there is water, Jupiter's moon, Europa, has basically all the conditions required for life. And as far as we know, there might be life under there. It could be very simple, like unicellular life, or it could even be more complex. We don't know, and that's why this is one of NASA's biggest targets for searching for life in our own solar system. Now, I mentioned liquid water. water to exist, right? It would evaporate and become water vapor. And water vapor is not in Lockheed, right? We want liquid water. So if you're too close to the sun, like this planet here, it's going to be too hot, and you will not have liquid water. If you're too far away, it's going to be too cold, and all the liquid water will freeze and it will become ice. Again, not good for life. But somewhere in between, there is this certain distance or this range of distances where the temperature will be just right for liquid water to exist. We call this the habitable zone. It's also more colloquially known as the Goldilocks zone because the porridge was not too hot, it was not in fact too cold, it was just right. Now, the habitable zone size changes depending on what kind of star you're around, and I have 3 examples of that here. In the middle, we have a sun-like star, so just think that that's the sun. That's our system right here. At the top, we have a hotter star, and at the bottom, we have a cooler star. Now, starting with the top star, the habitable zone is that green ring that we have here. And we notice 2 things immediately. The first one is that the habitable zone is farther out from its star. And that makes sense because it is hotter, so if you were at the same distance, it would be hotter. So that pushes the habitable zone out farther into the solar system. The other thing might be a little harder to tell is that the habitable zone is a little bit larger. Its radius is a little bit bigger. And this is important because the bigger the habitable zone, the more likely it is that a planet will form within its region. So that's a good thing, right? Because the more planets that form within the habitable zone, the more likely it is that life will develop on one of those planets. However, someone probably knew that however was coming. Hotter stars have one major issue, and that is that they burn their fuel very, very fast compared to what our sun does. These higher mass, hotter stars often will last between like 100 to 200 million years. That's not a long time in the grand scheme of things when it comes to, when we're talking about billions of years, right? We only just came into the picture, like I said, a few million years ago. So it took 4.5 billion years for intelligent life to form on the Earth. But I'm telling you, in 100 to like 200 million years around these hotter stars, their fuel will run out and they'll go supernova. They'll blow up. And the chances of intelligent life forming after that are 0, right? So because of that, we don't really like to look around these hotter stars for life because the odds of intelligent life forming within their lifespans is on the lower end. There's also not that many of these hotter stars. They are the rarest stars, these more massive ones. Now, the cooler stars have one major thing going for them, is that they're everywhere. About 80% of all stars in the Milky Way are these cooler red dwarf type stars. Now, you'll notice about the habitable zone, it is a little bit smaller than the... That means that there's less opportunity for a planet to form within that area. That's fine. And it's also closer to the star. And that leads to other issues. When a planet is that close to the star, there's going to be gravitational interaction between the star and the planet. What will happen is the gravity of the star is going to slow down the planet's rotational period, like how long it takes for a day to happen. And what will happen, based off math, we don't have to go into too much detail about that, is that the rotational period will match the orbital period, so how long it takes to go around the star. And what happens, or what that process is called, is tidal locking. Now, tidal locking is probably not a good thing for planets. The reason is that one side of the planet, when these orbital periods and rotational periods match up, one side of the planet will always be facing the star, and the other side of the planet will always be facing away from the star. This could mean that one side is perpetually on fire and you're melting, and on the other side you're frozen. Both of those are probably not good for life, right? Now, there is a chance that somewhere in between those two areas is its own little Goldilocks zone where the temperature is just right for liquid water to form. And that's what we have in this image here. There's also a chance that if the planet has a thick enough atmosphere, it might be able to regulate the temperature around the planet. So instead of having two extremes, it might have like an average effect. So maybe there is liquid water everywhere. but it's hard to say. We don't have enough data on these kinds of planets to know, but we are looking into that. But how do we find planets? How do we find these planets that go around other stars? Well, there are a handful of different methods for that. In fact, that could be its own presentation. So we're only going to talk about like the big one, probably the most successful or the most famous one. It's called the transit method. And what happens is in these kinds of systems, the planet will pass directly in front of its star from our perspective on Earth. And we will be keeping track of the star's brightness with time. And what we end up seeing is that the brightness starts to decrease. We get this dip in the system's brightness as the planet passes in front of its host star. Based off the depth of this dip, based off how long it is, based on how frequent these are, because this will happen every orbit, at least once per planet. Mass based off that. If we have mass and we have radius, we can estimate its density. And that's important, because we can figure out what this planet is made out of. If it's rocky, just like the Earth, right? We think rocky planets are better than gaseous planets like Jupiter because, again, if it works here, why not elsewhere? We don't know if there's life on Jupiter, probably not, I don't know, but there is life here, so we're looking for rocky planets. Now, the most famous tool for finding planets with this method is the Kepler Space Telescope. And it has been very successful in that endeavor. These are just a handful of the multi-planetary systems that Kepler has discovered. Blue means that it is close to Earth in temperature, and you can see that there is a size scale up at the top left. So you can see all the different kinds of planets that we have. Like there's some that are really hot, like it's basically on fire, like it actually says lava. And we have some that are really cool, and then we have some that are really big. We have thousands of planets that we've discovered using the Kepler Space Telescope at this point. This is just a collection of them, but not all of them. So this is how we are looking for planets where life may form. But what if we want to find like intelligent life? Like what if we want to find like the other version of us out there? Looking for planets with the transit method tells you that there's a planet there and it might be in the habitable zone and stuff like that, but it doesn't tell you that there's life necessarily. So we have other ways of looking for that. One thing is we look to what we send out into space, because we do send things out into space, and one thing that we send out all the time, sometimes on purpose, sometimes by accident, are radio waves. We send out radio waves out into space. So what we did here on the Earth is we built these giant radio space telescopes, or not space telescopes, giant radio telescopes that are looking for signals coming from space that are some unambiguous source that clearly can't be something from nature. Like it has to be some repeating thing that like only some intelligent civilization would have made. This telescope here is very famous. It's known as the Arecibo Observatory. It's also very much destroyed now. That happened a few years ago. They were decommissioning it, and before it even like fully closed, that top part right there fell and destroyed the rest on the bottom. But we do have more of these, and they're still actively searching for radio signals. We haven't found anything yet, but that is part of the search, right? And there's a lot of data to go through. Now, I said we were going to try to estimate how many intelligent civilizations there are in the Milky Way right now. And there's a fun thought experiment to do that. Now, I'm going to show you the name of this, and you might get scared for a second because it's called the Drake equation. Notice it has the word equation there. Equation means math, and math can be scary. But I promise you, it's not that bad, okay? It's going to be multiplication, a little division. And I'm going to walk you through it. Don't take it too seriously. We're just estimating. He's making a face right now. He's scared, right? Okay, what is the Drake equation? I'll give it to you. It is n equals n star times fs times np times fe times fl times fi times lc over lmw. The exam is tomorrow. I will see you all there. What does any of that mean, right? That's just a bunch of letters. Well, I'll talk about what each letter is. Now, n is the thing that we're solving for. That is how many intelligent civilizations there are in the Milky Way right now. That's the thing that we're going to try to estimate. And I emphasize right now, not 1,000 years ago and they're gone, right now. N star is the number of stars in the Milky Way. And we have good estimates for this based off all the observations we've made. We know that there's roughly between 100 to 400 billion stars in the Milky Way. It's a range, right? One's 4 times larger than the other, but when you're dealing with really big numbers like that, being off by a factor of 2 or a factor of 4 is not that bad, right? When you're dealing with these big things. I'm going to pretend that I know everything, okay? And you're going to have to pretend along with me. And I know for a fact that there are exactly 200 billion stars in the Milky Way right now. So that is the number we will plug in to our equation. Let's see. Fs is the fraction of these stars that are sun-like. Similar temperature to the sun, similar size. It's called a G-type star. Again, based off observations, we actually have a good estimate for what this number is as well. We know that roughly 7% of all stars in the Milky Way are like our sun. So we're not like the most common thing, but we're also not like the most special thing. We're kind of average when it comes to that. So I take 7%, I turn it into 0.07, that's 7%, and I plug that into our equation. Next, I combine these two into one thing. We have NP times FE, and this is the average number of Earth-like planets per sun-like star. I think that speaks for itself. What does that number end up being? Well, again, based off the observations we've made with the Kepler Space Telescope and Kepler's successor, which is the TESS Space Telescope, we have a rough idea what this number happens to be as well. Based off our data, we know that there are about 0.65 Earth-like planets per sun-like star in that star's habitable zone. So less than 1 Earth-like planet per sun-like star in the habitable zone. It's still a good number. I mean, 0.65 is not that bad. It's not in every single sun-like star that we see one of these planets. FL. This is the fraction of those Earth-like planets where life forms. Now, our equation has just changed quite a bit because those first few understand what those could be or have ideas as to what those could be. We have no idea what that number is. None. Because we only have one place that we know of currently where there even is life, and that's right here. So I don't have data for you on this. At this point, this Drake equation is very much an approximation, and it is my approximation, because I don't have data on it, and I'm just going to give you this number. I said that 80% of those planets that are in the habitable zone of a sun-like star that are Earth-like will form life. Why did I choose 80%? Well, personally, for me personally, I think that if the conditions are right, that life has a tendency to come out. That's my personal belief. I think life is a very resilient thing. So I said 80%. Maybe something happens and 20% just don't make it. I don't know, but that's my guess there. Fi is the fraction of those planets where intelligence develops. For that, I don't have an idea there either. Liam's laughing, he knows. I said 50%. Personally, I think intelligence is this like good evolutionary trait that like an animal would want to develop. I mean, we are like the dominant species on this planet right now, not to brag, right? So my guess is that 50% of those planets will form intelligent life. Maybe they got hit by an asteroid, or maybe they, got sucked up by a black hole. I don't know. So maybe not all of them make it that far. I mean, dinosaurs got hit by an asteroid. They died of acute asteroid poisoning 65 million years ago, right? They didn't make it to form intelligent life. Like we're the first, species that really has. But I'm a little more optimistic, and I say 50%. Now the last piece, LC over LMW. This is the lifetime of a communicative civilization over the age of the Milky Way. So LMW is the age of the Milky Way, and LC is how long that civilization is transmitting for. Now, LMW, we actually have a good estimate for that. We're back to good estimates now. That's 4.6 billion years. So that's good. That's good. LC, this is the biggest wild card out of all of them. I can say anything for this. In fact, that's basically what I decided to do. I came up with my own number. Personally, I'm not that optimistic that a species will be transmitting for that long. Now, there's a couple reasons for that. One is that what if the species develops some like hyper-intelligent form of communication that we just can't detect? well, technically speaking, we can't detect them anymore, so that counts as they're no longer communicating with us. But I take the more pessimistic route, and I think that they just blew themselves up way earlier than that. So for me, I said LC is 9,000 years. We have nuclear weapons on the planet, right? We could destroy the planet if we wanted to. Maybe we get past that, but then we develop some super cool energy source, and we're like, this will solve all of our problems. I turn it on, and I'm like, it works, and the whole planet blows up, right? That wouldn't be good. So I take the pessimistic route and say 9,000 years. That's actually not that bad. I mean, we're not close to that yet. So you won't be there for when we blow up the planet, right? But I say 9,000 years. Could be longer, right? So if I take all of these numbers that I gave you guys, and I plug them all into the Drake equation, what does our Star Wars-esque intelligent civilizations are there in the Milky Way right now, assuming I know everything? The answer is 7. That's not a lot. That's not that exciting. But again, I made up half those numbers, right? Those were like the bottom 3 like variables. That was my personal opinion. I could be hysterically wrong. What if it's not 9,000 years? What if it's 10 times that? What if it's 90,000 years? Well, it's not 7 anymore. It's become 70, right? That's a little bit bigger. What if it's 10 times that? Well, then it's 700. 10 times that, it's 7,000. We have no idea, especially for LC, how long a civilization will be transmitting for. This number could be 7 million, for all we know. But again, we're going to pretend I know everything. And we're going to go with 7, and we're going to figure out just how hard it is to find these civilizations. So I have the Milky Way. I hate to ruin the fun, but this is in fact not the Milky Way because we live in it. So we haven't actually taken a picture of it. So this is a galaxy that looks what we think the Milky Way looks like. So just pretend it is for a second. So the Milky Way is 9,000 light years in diameter. That means it takes a beam of light traveling at the speed of light 90,000 years going from one end of the Milky Way to the other. So it's a big place, right? It's not as big as the observable universe, but I mean, it's a big place. Now, I'll take that away. I said that there are 7 intelligent civilizations out there right now, and that includes us. I mean, if you want to include us, right? I mean, I've watched some YouTube videos before, and I'm starting to doubt if we count as intelligent, but let's pretend that we are. And I'm going to take all of those civilizations, and I'm going to evenly or equally distribute them throughout this galaxy. We don't have to make this assumption. This might not reflect reality, right? Who is to say that in the middle of the galaxy is like a hospitable place for life? There's a supermassive black hole there. It's spewing radiation. There's all these stars going to and from. There's these smaller black holes everywhere. There very likely probably wouldn't be life in that region, but we're just going to make the assumption that it is. Now, I put these orange circles there because they look nice. These orange circles are the unshared area of each intelligent civilization. So there are 7 of them. This is, the area of the galaxy divided by 7 gives you these 7 circles. And you don't have to worry about that too much because using math, that scary thing, I can use this to figure out the distance between 2 civilizations, like the 2 neighbors next to each other. And that ends up being 34,000 light years. Okay. Pretty far, right? So let's say this top civilization sends out a radio signal to that one on the middle left. We'll say that that's us, just for fun, right? It takes that radio signal traveling at the speed of light 34,000 years to get to us. Now let's make the hefty assumption that we live forever, like our civilization isn't going anywhere. Like, never gonna die, like that's great, right? That signal would take 34,000 years to reach us. I told you, based off our Drake equation, where I know everything, right, that LC is 9,000 years. That means that that civilization has 9,000 years, where they'll send that signal, and then they'll die. So by the time we receive that signal, that civilization has been dead for 25,000 years. That's crazy, right? Imagine. That makes it so hard to talk to anybody, right? Because by the time the message gets to you, they're not even there anymore. They change zip codes permanently, right? We're basically receiving echoes from civilizations that are in the past. And that's, again, assuming that we're even here in 34,000 years. I made that hefty assumption. They might send a signal and we might not even be here to receive it. That makes detecting life in the universe much harder. But again, this is assuming that there are only 7 civilizations. What if this number is much more than that? What if it's 70, 7,000? You know, all those different versions of 7. All of a sudden, they would be much closer to one another. And then it might be easier to detect a signal and then transmit one back and actually get a conversation going. Also, we made this hefty assumption that they're, equally or evenly distributed throughout the galaxy. What if they're all just like right next to each other? What if there's just one part of the galaxy where like 7 civilizations are like within several light years of each other? That would make sending a message very easy, right? It'd be like a 4-year, 5-year reply, or 10, I guess you have to double it to and from, right? But, again, if this life in our galaxy, if it looks anything like this, it'd be hard to communicate with one another. That's what makes the search for life so difficult, if it is this rare. Now, we made the assumption that these are all Earth-like planets around Sun-like stars, and that's where we got our Drake equation. But, who's to say that that's right? There are a lot of different places out in the Milky Way that are very different from the Earth. In fact, one important fact is that most stars have at least one companion. So one star goes around the other star, so they're traveling together. So that's the majority of stars. So could a planet, exist going around these 2 stars at the same time and be stable enough to support life? So that's research that I've done in undergrad at Stonehill College, and research that I'm going to be continuing to do after I'm done with my black hole stuff that I'm working on. So right now, I have a planet denoted with that green circle, and its 2 stars are the orange and blue, respectively. I hit play. We'll see that the planet starts going around the orange star, goes around once, goes around again. But oh no, it's going around the blue star now. And now it's going around that one. It's not very stable, right? Your seasons may look a little strange. On the right, we have the temperature of the planet in Kelvin. I apologize for Kelvin, right? Why didn't I use Fahrenheit? Well, because we're scientists and we like Kelvin for some reason. So for those who don't know, liquid water can exist given an Earth-like atmosphere at these temperatures denoted by this blue region. Notice we are not always in that area. This is like the ultimate version of that Katy Perry song, right? Like it starts off and it's too hot, right? And then it's too cold. It's yes and then no. And it's in the habitable zone. Now it's out. And then finally, last but not least, it goes up and then it goes down, right? I have like family and friends watching this online right now. If you listen very carefully, you could hear them all sigh with disappointment at that joke. But I was going to make it regardless. So that doesn't look particularly good for life, right? Because, at one point you're frozen and then you're on fire and melting because it's like 1,000 Kelvin. Not great for life. But this is an example of an unstable orbit. It's being sent back and forth between the 2 stars. In fact, at one point, or later on in the simulation, the planet just gets thrown out of the solar system entirely. But there are stable orbits too. We have this one on the left. It's an S-type orbit where the planet goes around one star. And then on the right, we have a P-type orbit, where this planet goes around both stars at the same time. Both are interesting, but S-type is kind of just like what we have in the solar system. It might change the orbit a little bit, but P-type, that's more fun. So we've been focusing on P-type because that's a little more unusual. Now, in these 2 plots, I have the habitable zone denoted with this blue ring. And I have the planet starting in the habitable zone. And on the left, we see that its orbit isn't quite circular, but it always stays within the habitable zone, right? That's good. It's always within that range where liquid water can exist. But the stability of the planet's orbit is going to depend on a bunch of different factors, one of which is how far the 2 stars are apart from one another. So what I did on the right was I moved the 2 stars apart just a little bit. It's even hard just looking at it how far I moved them apart. They're pretty close to where they were before, but I moved them just a little bit. And now let's see how the planet's orbit changes. Okay, oh no. Okay, we're not in the habitable zone anymore. Okay, we're back, we're fine, right? And okay, we're on fire again, and now we're taking a nice trip where we are, in fact, a snowball. Fun fact, this is also not a stable orbit. Eventually, this planet also gets chucked out of the solar system if I ran the code for long enough. So this is something that we're actively researching. We're trying to find this relationship between the masses of the planets, the sizes of their habitable zone, their separation between the two of them, to see if a planet can exist in its habitable zone and have a stable orbit and have the conditions needed for life. Now, how do we sum up everything we've talked about tonight? So we talked about the conditions for life. We talked about Lockheed, and we used Earth as our example. We talked about the search for life, the Kepler Space Telescope looking for exoplanets. The Arecibo Observatory was looking for radio signals, not anymore, unfortunately. We went over the Drake equation. We definitively found, you can tell all of your friends that there are 7 civilizations out there in the Milky Way right now. Please don't tell them that. I'm not right. I'm definitely not right. But regardless, we made that calculation. And we probably are leaving here with more questions than answers than you wanted, right? Like, I'm sure you wanted me to just pull out an alien and be like, there it is, there's life in the universe. But, I don't have those answers. And that's what makes searching for life in the universe such like it's on the forefront of science right now. It's okay that we don't have these answers. That's what makes the exploration for it more exciting. Now, I'm sure you still want my personal opinion, right? You want to leave with something that you can tell your friends, like, he said that, like, that's good. My personal opinion is that the universe is a big place. It's an old place. I think, based off those facts, just how old and how big the place is, it is a statistical certainty that there is life somewhere out in the universe. Somewhere. Now, I showed you that it can be very hard to find, and they could be very far away, and they might not even last long enough for us to talk to them. But I do think that somewhere there is a value of n greater than 1, greater than just us. But what if it is just us? That can be a bit of a scary thought, right? And that's okay. You look a little nervous thinking about that right now. That's fine, right? It would be upsetting to know that, but at the same time, I think it can be looked at from a very positive outlook. It means if we're the only people in the universe, that we're all we've got, right? So might as well work together because no one would be coming to help us. So we might as well help each other. So that's all I've got for today. If you have any questions, thoughts, comments, statements of outrage, now would be the time to ask. But thank you. Anybody at all? Yes.
For those binary systems,
Mm-hmm.
the habitable zone wouldn't end up being just that circular ring, right? Because the temperature depends on how the radiation from both stars acts.
Yes.
That is kind of dependent on your distance from either.
Mm-hmm. At a far enough distance, you can approximate it as just a single habitable zone. But I do have part of the code which I didn't show you, which is always calculating how much energy it's receiving from both stars with time. So it tells you the exact temperature. So that habitable zone version was more or less to show you how stable the orbit was and it staying within that region. But that's not like a hard version of as to what the temperature actually is. Mm-hmm. Anybody else?
So what's our best chance of finding evidence of carbon compounds in liquid water on one of these planets that you've shown us?
Would it be, I feel like I'm being quizzed right now because my advisor asked, would it be the James Webb Space Telescope maybe? Looking at the atmospheres of these distant exoplanets, looking for signs of water in the atmosphere? Could be one version, could be one version. I mean, finding a radio signal that says, hey, would be nice as well. But yeah, I don't know what necessarily the best answer is. And the other thing you have to take into consideration when talking about the radio signals is we speak English. What are the odds they do too, right? Probably the language that would be used, it's the language that we send out our own radio signals on purpose to places hoping that someone would actually receive them. And what we do for that, because right, they're not going to speak English, is we send math. We send like these little equations and ways to solve for things. That's our language, because math is universal. Any civilization could, technically speak.
It's the same in every country.
It's the same in every country, yeah. 1 + 1 is 2, right? Anybody else? Okay, well, thank you for your time.